Hi everyone, I want to go over the homeworks from Euler and Hamilton parts. And so the first one was a question very similar to the original question that Euler was trying to solve. And that is, you have a city designed this way with the two rivers, or, well, perhaps one river splitting basically more. And the question is, these bridges, is there a walk through the city so that you cross every bridge exactly once? Now, okay, we know how to do this. As in the way that Euler solved this, we first of all have to make a graph of that. And what is perhaps a little bit counterintuitive is that the vertices are going to be the regions. And there are four regions. So I'm going to call them A, B, C, and D. Right? The river splits the whole plane here in four different regions. So these become the vertices of the graph. So, okay, let's make the graph. So we have A, B, C, and D. And now every bridge means an edge. And since there are, for instance, two bridges from B to D, there will be a multi-edge. But okay, let's start with A goes to B. And from A, you can also go to D. Don't forget that this whole region is D. So this, and this whole region is A. So from here to here, you go to D. Okay? So we have these two bridges. From B, there are four bridges. So one goes to A, we have that already. One goes to C, okay? And then two go to D. Don't forget, we have two. So we do this, okay? And then last one, because the C, from C, you can go to B, to N, and to D. There are only two, right? Okay. So we have now 1, 2, 3, 4, 5, 6 edges, 2, 4, 6 bridges. So, right. We have our complete graph. And then the next thing we have to do is find the degrees. 2, 4, 4, and 1, 2, 3, 4, and 2. So what does this tell me? All even, no, let me put it that way. No odd degree. Sorry. No odd degree. And this means there is an Euler circuit. Now, allow me to quickly. Okay. So then our algorithm says, okay, just pick any vertex you want. I'm going to pick A and make a walk. So here is our A, and I'm going to do the walk on the graph. So I'm going from, let's just make a simple walk. Well, perhaps not a simple, let me walk this way. A to D, C, B, and then back to A. Okay, so we write up A to D to C to B to A. Okay, and we are back in A. So what we have now is some of these edges are no longer accessible, right? Remember, whenever we come, we close a door. Whenever we go, we close another door, and these two doors are closed here. But we have still this here. Now, moreover, we have to pick on this path two that we have already not used. That still have edges. So we pick B here, and here we have there's no choice. We have to from B, do D, and then come back over this. Let me do the slightly different color from B. Oh, no, I want to do it here. From B, and then back D. Okay, and then the whole thing is we put these two together in here, right? So once in our first part we go A, D, C. So put together here. This is the last step. A, D, C, B. Once we reach B, say, oh, wait a sec, I have a detour. D, B, and then A again. So if you want, I'll plot it out for you. I'll do it in a little bit in a dotted line here. So the path that we would walk is from A, we go to D, and then to D we go to C. Okay, so we go C, and then from C we go to B. That can only be it wants to do smart things and I don't want it to do smart things. B, and then from B I go to D. Okay, and then from D I go back to B, and then I go to A. All right, so, and depending on how you chose things, your path might be realistically a good path. This actually is not a bad walk, but sometimes if you put things together differently, then it's a bit awkward walk that you have to go all the way to that bridge and then come back to that bridge and so on. But that's not the issue here. That is for what we see in today's lecture, right? Okay. So, all right, let's go. The next problem is about drawing, number 14. So we have this picture here, and the question is, can you draw it with not lifting your pen? Now, of course, you see me lift my pen all the time. I'm going to make it a bit bigger here, like make this the outer one. And then there's also even a line in between here. I want to be a little bit more careful here. This is, okay. And the question is, can you draw this? Obviously, I didn't, but can you? And how to do this is you make a graph out of this. The line segments will be edges, and the end of the line segments will be the node. So this means in particular that this is also a node. This is where one of the segment ends. A crossing is always an end of a segment, right? So of course here also we have corners also are ends of segments, but there are quite a lot of vertices. This is a quite a big. It's not a big graph, but it has quite some edges. Okay, so the next thing we need to do is the criterion for Euler. What we need is it suffices to find an Euler path, because there's no stipulation that you have to draw the whole thing and be back where you started. Why would anybody care about that? If you can, sure, but you don't have to. So. Let's calculate degrees. Now, no, we haven't seen that much, but sometimes there are guys with degree 1, right? So this is an example where graphs that has degree 1 here. This is degree 2, this is degree 2, and the middle one has degree 4, and it's rather symmetric. So I'm not gonna. We see, you all see, I think, immediately that these are the degrees, right? So what we see is that all degrees are even except the outer ones. So there are 2 odd degree vertices. So this means an Euler path, not a circuit. The previous one was a circuit. However, how do we solve this? We make a new graph. I'll call that the green graph. The green, it's the official turtle name that one uses, an augmented graph, where I add one edge connecting these 2 odd degree ones together. So that's one more edge that we have, and now this one has an Euler circuit. And I solve the problem as before, but the only thing is that whenever I use the green edge, I have to mark this, that I keep track of this. Okay, so then let's start our procedure, right? So the procedure is always you pick a vertex that still has edges coming in and out, that still has a pick. I'm just going to A, and then you pick also, I'll do this in one step, a path through A. A circuit through A. Now, you might be worried a bit that if you start walking and you can get yourself in trouble, so to speak. If you might think, oh, if I go too deep in here, I can never get out anymore. Well, that's the beauty of this theorem, says that as long as all the degrees are even, you can always get back to your starting point without reusing any of the edges before. In other words, you can close the doors, don't worry about it. It looks like you're stuck, but you will never be stuck. I mean, imagine this is a labyrinth and you have to get out of there. It looks scary though, right? You say, oh, I'm going to close this door, and what now? I'm going in the wrong direction, I have to go this direction. No, it doesn't matter. Now, I'm just going to pick a path, and I'm going to take an obvious path. I'm just going to go all the way down here. I'm going to say, okay, let's walk all the way down here and then go back. That is clearly a path starting at A, and eventually I return to A. So let's write down what that is. Oh, okay. Sorry, what is A? Right. So A, B, C, D. I had already named these guys in my head, but I forgot to tell you what the names were. So A, I, J. I'm not going to sing the the ABC song because I'm a very bad singer. O, P, Q, R, and S. All right. So I start, pick A. I want to say pick the degree 1, right? And then I'll go down. So that would be A, C, F, I, L, O, R. Oh, I haven't given this guy a name. T. T. And then I go back to A. Sorry. Okay, this is a fine, but I'm not going to do it. It's fine, but I'm not going to do it for a reason that I'll explain later. Because what I want to convince you of. Oh shoot! I have to be careful. This is too big. Sorry. Allow me to retract my first proposal. It is fine. I didn't do anything wrong, but it's just I want to show you things. I'm gonna pick a random. I want to show you that by picking random numbers, random vertices, and random paths, you always work. It's not that you have to be paying attention and say, oh, make sure that so randomly. Give me a letter. Okay, the way I'm doing it, you cannot see it. I'm just gonna scroll to a page, and the first letter on the page is a B. So I'm gonna start from B. Okay, so pick B. I'm a little bit running out of space. This graph is a bit big, so I'm gonna start doing this here. So pick B. And now I'm gonna take B, and I'm gonna say, okay, B, I'm just gonna go around, guys. That's the simplest thing I can do. That's what I'm gonna do. All right, that's fine. You do that. So B, so that is B, C, D, S, R, Q, and I'm back at B. What is the next thing? Now we have to take, we take a vertex, but a vertex that is still in play. B, D, Q, and S, the outer corners are no longer in play because they have no edges in and out anymore. But I cannot just pick anything. I cannot just pick a guy here. I have to pick something that has already been walked through, and so this is in this case C and R. So I'm going to take C. Okay, I pick C, and then my walk is I'm going to go this time counterclockwise because the other first time I went clockwise. And I'm just going to go up and all the way around and all the way up and up and up. So why not? Okay, so that is C. Then I go to A, then I go to T. But this is the green edge. And I said I have to keep this AT, this is using the green edge. I want to mark this somehow. Whichever way you do it, I'm going to do it using green color here, writing that this A and T are connected to a green edge. And we'll talk about why we're doing this, right? We have explained it in the video, but in the review, I will also explain it in the view, but let me explain it here now one more time at the end. So then T, then I was going up, right? R, O, L, I, F, C. I was going to C. Okay, great. So now I have to pick anything that's still in use, but it has to be already on one of the path circuits that I have run on. So I'm running circuits, and I need to pick something on the circuit that is still available. So for instance, why should I not take E? Sure, I could take E and I have a path. So if this E, I would have a path going around there, and then I would go down the path, and eventually I have to put everything together, right? So imagine a path starting with E here. And so this has to now be put inside. So I start with this one, I put, what I'm gonna do is replace this C by this whole thing, and then I have a path starting with E, but there's no E that I can replace it in. So that is the reason why we have keeping to take things on paths that we have already used. And there is always something available because the graph is supposed to be connected. Okay, in this case we have three choices, F, I, L, and O. Okay, I'm just picking L. So pick L. And let's do again a walk around. Why not? I do it in blue. And we're going to go again clockwise, say. So this would be L. And then what was I doing clockwise? So I went to K, H, I, J, M, and back into L. Okay. Now pick something that is left. Well, it has to be f of O, because there's nothing else left anymore. Well, E and G and N and P, but I cannot take those because they are not being visited yet. I can only use visited guys, so I'm going to pick F this time, and I go around again, say counterclockwise. E, N, O, P, G, and back to F. So let me show you what this is. So this is this path, right, that I'm walking on. All right. And now you see everything is used. I'm done. I'm put everything together. So how do you do that? Well, we start with the top one, and we're gonna. It's when we reach this vertex in the first part. I'm gonna replace. I'm gonna make a detour. So here we go. B, C. I reach C. Okay. This is now where I use the detour given by the second part. The detour is we have this. The next one is an A, but it's a green T because they are connected to that green edge that's not part of the original graph. And then comes R, O, L, I, F, C. Okay, so this is the thing. This C is now replaced by this whole expression. I'm back in C, and now I continue until I meet, okay, right, and then I continue. C, D, S, R, Q, B. One step at a time. Sometimes you can do two at a time, but you see here I couldn't. The next one I have to incorporate is this L, but it was not in my top part. It is in the second part. So now in this new circuit, I should say circuit, in this new circuit there is an L. Here's the L, and so this L will be this whole little circuit will be replaced when I reach this L. Okay, so this is B, C, A. Oh, I have to do this in green. Okay, A, T, R, O, L. So here I'm reaching L, and I will go this little detour here. K, H, I, J, M, L. Back in L, I can continue my previous work. I, F, C, D, S, R, Q, B. I hope you see what happened. Okay, so this part is now gone with, this part is dispatched with. This part, these three parts have now all joined, so there's one part left, this F. So where is an F in my part? It must be there, by the way I chose it. Yes, it is here. And so this whole expression will now be replaced there. So that will be, I'm not going to copy this all the time, so I'm going to do a little cheating here, and I'm just going to squeeze it in. I'm going to say, okay, guys, this is what I do here. F, E, N, O, P, G, F. Okay, so we have now a circuit from B going to B. Now notice that this is actually, you should think of a circuit is a circle, right? So this B is the same as this B, okay? But anyway, so we have this, we go this, and then we go F, and then this way, okay? This is the path listed. I could circle it too. But this path uses the green circuit. This green circuit uses the green edge, which I'm not allowed to use. How can I avoid that? There's only one way to avoid it in this particular circuit, is to start at T, walk the whole way, and end at A. That is avoiding that green path. So that's the last step. So this is a circuit. This is a circuit in the green graph, right? Because that's what I've been doing all the time. So now we need a path, an Euler path, in the original graph, and that means I have to start from T. So I cut, as you want, the path from here, the circuit, and start there. So we have T, R, O, L, K, H, I, J, M, L, I, then I go down there, F, E, N, O, P, it's a G, show me that's a G, G, F, C, D, S, R, Q, B. B. Why? Oh, no. Are you stopped? Done? No, because hey, there's still a little thing here, right? Don't forget that part. What now? B? No. Remember, this B is just, this b is the same as this b. That is because the way that we have to write down the circuit, we have to write the endpoint as well as the beginning point, right? But if you will be able to write this on a circle, then we would write b only once. So the b comes only once. The next one will be c, and then we will be a. So we have to start here and end here. So this is the start and this is the end of our walk. And we knew that. We know that it's always going to go from the odd degree to an odd degree. And okay, this is one walk that goes from T to A, but of course there's a walk from A to T, right? That's just going that direction. Okay, and this is not the only solution. And I don't want to trace it because it's probably quite long to figure out how it is. Now, so the last question that I want to look at is number 47, right? Number 47. And it asks to check two of the conditions of existence. So the existence of Hamilton paths. Hamilton circuits, sorry. Hamilton circuits. And although there are very often Hamilton circuits, it's hard to predict it. And so the two criterion is two theorems. One is by a fellow called Dirac, who actually is a son of the famous quantum physicist. And Dirac's theorem says that if you have, so both are for if a graph with n vertices. So n is the number of vertices. Dirac says if the degree of every vertex is at least half the number of vertices, which is quite a lot, actually. We'll see it in examples. Or says, well, okay, what I need is that the degree of A plus the degree of B is at least n, but for A and B not adjacent. That is a weird condition here, and I'm a bit worried that I might have said it in the lecture the wrong way. I didn't do any problems on it, but we'll see it now. So the A and B should not be adjacent. Okay, not adjacent. We will talk about how we do this. Now, there is one thing that the book already mentions, and let me explain it here quickly, that if the Dirac holds, the Dirac condition holds, the OR condition holds too. Let's think about that. If every vertex has degree at least n and a half, then these two, each of these are at least n and a half, so if you add them, it's at least n, and that's exactly what the condition says. So if Dirac holds, OR automatically holds. The OR condition. The Dirac condition holds, the OR condition holds. For all vertices, not just for those that are not adjacent. Okay, so let's look at the examples. There are rather small graphs. It is rather quickly to check. So the first one is a house. Okay, we have a house like that. And so this all has to be the degree. So here n is 5. This is A, right? And n is going to be 5. Only in the last one it is going to be a different number, I think. N is 5. Okay, so let's calculate the degrees. 2, 3, 3, 2, 2. Now, if n is 5, what does this then mean for our case? So let me perhaps do it. N is 5 here. So in our case, this means it has to be at least 5.5. But a degree cannot be 2.5. So it means actually it has to be at least 3. So the condition here is that the degree has to be at least 3. That's the Dirac condition for n equals 5. Is that the case? No. So Dirac condition does not hold. No. What about the OR condition? That is a weaker condition. It's a weaker condition, right? Because the Dirac implies OR. You have to think a bit about that. So how do I check that? So, okay. What is the green, the black graph? The lines are the edges. So this gives me exactly the vertices that are adjacent. So how do I find the ones that are non-adjacent? Well, that is what is sometimes called the complementary graph. That is, you draw now edges to everything, all the edges that are not there yet. So for instance, this is an edge that is missing. This is an edge that is missing, this is an edge that is missing, and this is an edge that is missing. If you look at the whole picture, both together, the black and the purple, then you have to have a complete graph. Remember, this would be then K5. The black and purple together is K5. And in particular, the reason I'm saying that means that each vertex has degree 1 less than 5, 4. So to make sure that you have everything, you now check, do I have 4 in each? Yes, there are now in each 4 come down if you combine the two. Now, the purple graph, so try to pretend to not, I don't want to erase it, but pretend to not see the black, but only the purple, is the graph of non-adjacents. And those have to, and there we have to have that the sum of the degrees must be equal to at least 5. So what I'm going to do now is write on the edge a number, namely I'm adding these two sides. Like for instance, like this edge, I'm going to give it a label. We have seen now labeled graphs today also. Oh wait, I'm going to give this the label consisting of the sum of these 2 degrees. So this will get label 5. So this get label 5. I'm going to write it on top of it that we see where it is. The other one, the other diagonal is the same, 5. But then the higher ones, they have only 4, right? It's 2 plus 2, and this one also 4. Now, for this to be true, all of these numbers that I wrote down have to be at least 5. So we have to have here at least 5. So ORA is not true because, for instance, these two are not adjacent in the original graph, but their sum of the degrees is too small. Okay? But then the last question is there a Hamilton circuit? Just because the conditions hold doesn't mean that there is none, and the answer is yes, of course there is one. These are simple graphs, very, well, simple in their easy graphs. Let me put that here. Hamilton circuit. A Hamilton circuit means you have to visit every vertex just exactly once, and I did that. So, although both conditions do not hold, there is still a Hamilton circuit. That tells you that these conditions are not very great conditions. And you'll see a couple of examples. The next one is B is the same house with one of the diagonals now also there. Now, before I even move on, what do you think? You think, is this going to be have a Hamilton circuit? Yes, because adding edges is just going to make it easier to find a Hamilton circuit. If you have already one, and that's the previous one, adding one edge is not going to change anything. So we know that there's going to be a Hamilton circuit. The question is now, is the Dirac and the ORA conditions? What about that? Okay, now the Dirac we can immediately dismiss because this has still degree 2. So Dirac, no, because there is this because of this one. This has degree 2. It's not the only one, by the way. There's also this one. These have degree 3, so they would have degree 3 or 4. They are okay, but it's this one that says no. But the ORA condition. Now, for the ORA condition, we should do again the complementary graph, which means fill up all the missing edges. This is this one, this is this one, and there should be one more. Yes, this one. Okay. And now calculate the degrees. So I should have therefore calculated all degrees. Sorry, here I'm sorry about this. I should have done this before I drew the purple. The red ones here are the degrees in the original graph, right? The black one. These were the original graph. So now the purple one. This I have to start summing the endpoints, degrees of the endpoints. So this would be 5, 2 plus 3. This one would be 5, 2 plus 3. But unfortunately, this is still 2 plus 2, 4. So also ORA does still not hold because of this guy. Okay, this is shows me that ORA doesn't hold. But there is of course a Hamilton circuit. We said that. Let's look at the next one. C. So we have now a slightly different graph. Okay, so let's write down the degrees. 3, 3, 4, 3, and 3. So what about Dirac? Dirac says every single vertex has to be a degree at least 3. Yes, that's the case. 5 over 2. But that means 3 is bigger than 5 over 2. So Dirac holds. What about Euler? So the Euler condition always requires you to draw this complementary graph. So what are the edges missing? Right? Let's think. There must be edges missing because we know that we have everything if the black and purple together have degree 4 at any vertex. So there's still something missing in the corners. Well, yes. Connect this corner to this corner and connect this corner to this corner. It's a bit harder to see, right, in the picture. You might be misled by the fact that we have this diagonal line and say, so the diagonal is there. No, it's not really there, right? This one is not part of the graph yet because we have a path of length 2, that's the diagonal, but not the diagonal itself. So these are the two. Now, let's write down the sum of the degrees of their endpoints. That is 6 here and 6 here. So Euler is now satisfied. It's at least 5. That's enough. Okay. Now, should we have checked it? Not really, because if Dirac is true, we know that Euler was going to be true. But okay, we did it. So then we have a slightly different graph. That's D. So this is this one, this one, this one. And now the degrees, let's calculate them again. 3, 3, 3, 3, 3, and 3. So Dirac again is correct. Oh, sorry, what I forgot to say, is there a Hamilton circuit? Yes, the Hamilton circuit, right, in the previous one. Okay, here, Dirac is true. Oh yeah, of course, sure. Dirac and Euler continuum holds. We know this one, but here is one, just in case you were wondering. So what about Euler? Well, again, because Dirac is true, Euler is true, right? So we don't really have to check it, but let's just check it. How would you check it? Now, we have 6 vertices, so to make the complete graph, we have to have 5 outcomes. So in each of them, 2 are missing. Which am I missing? I'm not connecting this one, and I've not connected that one. What is missing here? This one and that one. Then what I'm missing here is this one. This one is also missing that. And what else am I missing? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What did I do here? Something is... One, two, three, four. In the bottom one, what do I have to still do? 1, 2, 3, 4, 5, 6. No, some. This is. Oh, I see here. This is wrong. We have this already, right? Oh, okay. That's. I drew it. I meant to go there, and I went wrong. So now it's right. Everything is right. Okay. So now we have to write down the sum of the degrees, but we know what they are, right? Because it's always going to be 6. It's always going to be 6 because, well, they all have degree 3. So Euler also holds. Now, is there for a Hamilton circuit? Is it hard to find? No, it's not hard to find. Here, this one. All right. So that was that question. I want to add a very small, quick thing. It's going to take 10 minutes, perhaps. I didn't give it as an exercise. I give it as optional exercise. So the optional exercise is, I give quite a lot of exercises, I agree. It's the night tour problem. So that was question 59. So optional, that was question 59. And so we had this night, and the night. How does a night go? Right, to have I'm going to do the 59 is on a 3/4 chessboard. So here's a 3/4 chessboard. Now, and what is a knight? And if a knight is here, the moves that he can make is he can jump this way, he can move there, he can move there, or he could move here. Okay, a knight is always to go 2 in one direction and 1 in the other direction, whichever is possible. Okay, so that's how knights move. I'm sure that many of you know chess, but those that don't know chess, okay, that's how this works. Okay, so I'm going to use these. I'm going to give them I, J, K, L. And so I'm going to make a graph using these guys. I'm redrawing it. I could have drawn it on top of the same thing, but it is better. And let's now connect two vertices in this graph. So, okay, there are A, B, C, D, E, F, G, H, I, J, K, L. Let's connect them if there's a move, a Knight's move. A can go to J, and of course J can go to A. A can go to G, and that's the only two that from A you can go. From B you can, that's the one that I showed, you can go to I, you can go to K, and you can go to H. From C you can go to E, you can go one down, one left, two down, you can get one left, two down, and that's it. And then from D you can go two down, one left, or you can go two left, one down. There's a few more. I'm gonna draw them quickly. This one goes, and I can also go this move, and then I also have this move and this move, and I think this is everything. So let's draw the degrees. That's 2, 3, 3, 2, 2, 2, 2, 2, 2, 3, 3, 2. First of all, we see that there can be an Euler circuit cannot exist because too many degrees here. So if you read the question a little bit and the stuff before it, although that I just assuming what the rest of the is explained there, is that you can do a tour. A tour is what? You start in one of the squares and you jump with your knight around and make sure that you visit every square exactly once. That would be what's called a knight's tour. Okay, so that is so called that would be an. What that means, therefore, in terms of this graph, is a Hamilton circuit, because going from one to the other is exactly doing that. If you go from A to G, that's exactly making the move from the knight jumping from A all the way to J. Okay, so the question is, can you find a Hamilton circuit in this thing? Now, the OR condition, there are, look how many vertices there are. There are 4, 8, 12 vertices. So n is 12 here. So if you want to do Dirac, you have to have degrees at least 6, which by far we are not. And or if you want to do OR, they have to add up to 12. 2. That's never going to happen. The biggest is 3 that barely get halfway, right? So these criteria don't help me. Now, yes. So what we have discussed is that if you do a Hamilton, I'm sorry. A knight's tour. So a knight's tour means visiting every square exactly once. So what is this? I said, I'm so sorry, I keep missing these two concepts up. It's a Hamilton path we want. Hamilton path, not a Hamilton circuit. A Hamilton circuit will be visiting every square once and being back where you were. This has a name, it's called, I don't know why it's called that, a reentrant. It's a reentrant knight's tour, but let's not think about that. So I'm now looking for a Hamilton path. Now what we know, for a Hamilton circuit, I know this is not what we're looking for, but we know a very important fact. Now remember, a Hamilton path and a Hamilton circuit, as the same with an Euler path and Euler circuit, are going to be just one edge different, right? It is that you don't connect back anymore. The Euler circuit, remember, that's exactly here, in the original one, we had the path that we found, right, here, was not using this one extra edge. So from the Euler path, we could make an Euler circuit by adding one edge. And that's the same in the case of a Hamilton path. So let's think about Hamilton circuits. Now in a Hamilton circuit, you have to visit every vertex. Now the vertices of degree 2 have to be visited, but they have only two edges. That means whenever you come in, you have to go out that edge. And you have to go out using the other edge. So that means the two edges will all be used. Now, if you have degree 3 or higher, then you have to come in and go out. So it means one of them will not be used. 2 out of 3 will be used, right? So that we have to keep in mind. So there are 1, 2, 3, 4, 5, 6, 7, 8 degree 2. So at least in 7 of those, we have to come in and out. It might be that we start at 1 and therefore never have to come back, and then end in the other and never have to come back. So, sorry, I said 1, 2, 3, 4, 5, 6, 7. Sorry, no. How many are there? 8, right? It could be that I start in one and end in the other one, not using, therefore. So if I start and end in a degree 2, then those I will not use everything, but the remaining ones I have to use. So I'm going to look for, I'm searching for a Hamilton path that starts at A. It's not guaranteed that I will find one because it's a path, not a circuit. And a circuit I can start whenever I want, right? But a path gives me limitations. But I'm going to see whether I can start at A. That means I have to, let's start walking. Okay, I have two choices at A. So I'm going to choose this one for a reason. So okay, okay. Now, since I am in G, I have no choice. I have to go this way. Then in I have no choice. I have to take that one. Now in B, now I have a choice. Should I go, there are now two choices. Should I go to this guy or should I go to this guy? Okay, and that is the thing that we have to guess a little bit. And that's not obvious. This is not an easy problem. It has a star, which means it's not easy, right? So I'm going to K. Okay, so I could have taken degree 2 and a degree 3. The reason that I'm don't want to go to degree 2 because it will cut down my abilities. Remember, a degree 2, there's no choice. There is one edge in and one edge out, right? When you go to degree 2, you know there's no choice what you do. It's in the higher degrees you can choose something. So I had in B, I felt I have a choice and I want to make the choice. So I made the choice now and go to a degree 3, which again allows me to make a choice. But now actually the choices are, the two remaining ones that are adjacent here are both a degree 2. So that probably is not going to make a difference anymore. So I'm just going to pick one. And now a lot of the walk is fixed, right? Now, again, we have a choice here in C. Should I cross over? But if I cross over, I don't think, so I'm crossing over, I mean I go from degree 2 to degree 3, but then I'm getting a little bit stuck, right? You see, if I go to J3 here, then I can only go this way, which only can go that way, and that I wouldn't have visited these two. And if I go this way, and the other choice in J is to go that way, but that already ends my path. So I'm now deciding not to go to degree 3, but to degree 2. Okay, so I'm going to go 2. Oh, that's the wrong color. I go to degree 2. No choice. After this, no choice, no choice, no choice. And well, I haven't visited. No, I didn't visit J and H. Okay, so let's back up. Okay, what did I have the feeling that it did something wrong. No, okay, let's back up. So where did I make choices, right? The crossover choice. That was the first time that we had a choice in B. Let's take the other choice. Okay. Instead of going to a degree 3, let's go degree 2. Then I go this way. Now I have a choice again. Well, definitely I don't want to go to A. So I don't have really a choice. So I have to go to this guy. Now I have a choice, but it's both degree 2. Okay, I don't really know, so I'm going to go this way, this way, this way. The degree 2s never give me choice. Here I have a choice. Do I really have a choice? No, because B is already, I've visited B, so I should really go there. And now I should go there. And no, I shouldn't go there. Sorry, so that last one I shouldn't have done because I have already gone to C, but I have visited everything. So I found one. It's not obvious at all, right? So, and that is why these other questions are even harder to show that on the 4-4 it's not possible. On an 8x8 it is possible. And there's also a problem that tells you how to do it. We don't have a good method of doing it, but we have a good way of guessing how to do it. If you start from an, because it's, you can, the question is, can you start at a particular square and visit the rest of the chessboard from that square? And we have good methods to do it, but not, they're not 100%, not full 100% foolproof. And that's very often that we sometimes get algorithms that approximations that are often well, but sometimes don't. Last question, just very quickly. This graph, is this a bipartite graph? Okay, so think chessboard. What is a chessboard? A chessboard has two colors, right? So it has the black, white, black. So this is black. I'm going to make it gray. Black, 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 black. Now, what does any move of the knight? It always will change color, right? This means that any two edges in this graph will always have two different colors if they are adjacent. If these are adjacent, then one must be one color, the other must be the other color. So, in other words, if we color them, and here is the coloring, then we get see that no two vertices of the same color can be adjacent. Because if two of the same color would be adjacent, that would mean that you can go from one to the other using a knight, but the knight always changes color. When he goes, if he is in white, he goes to black. If he's on black, he goes to white. Okay? So this is a bipartite graph just from the fact that it comes from a chessboard. Okay.